Hello everyone, my name is Wayne and my Disney Infinity ID is Sumerian. Welcome to Fun with Logic, where we will be going into the toy box and doing some more advanced connections of the Creativa toys, just to see what we can make Disney Infinity 2.0 do for us. Hello everyone, this is Sumerian, and in today's video we are going to be talking about satellite receiver. And the great thing about a satellite receiver is that you can use it to send information in between separate toy boxes. And there's a lot of reasons you might want to do that. One of the most common ones is, say you have a quest you want to do in one toy box, and you don't want a second quest to happen in the second toy box until you've done the one in the first toy box. And a satellite receiver, you can actually send a trigger between the two toy boxes to let them know when you've actually completed the event. You can trigger the satellite receiver. Now, satellite receiver is absolutely great for that. They work really good, but one of the common problems you hear about, or you hear complaints about, is that there's only 10 different, I call them triggers, they're actually called stations in the toy itself, but there's only 10 different stations you can use. And I've heard a lot of people say that they want to send counts from orb collections or things like that between toy boxes so they can continue a collection challenge in the next one, and that's hard to do with only 10 stations. So what we're going to do is we're actually going to put together a way to send a much bigger number than 10 through to the next toy box using a satellite receiver. And what we're going to do is, you can see there's two states to a satellite receiver right here. There's turned on and turned off. And to me, that is basically a 0 and a 1. And if we consider the satellite receiver to not just be 10 possible channels, you consider it to be 10 on-offs, or in the computer world, you could consider that to be 10 bits. And if we actually view these stations as bits as opposed to just triggers, we can then say that with 10 bits, you can actually send 1024 different numbers. At station 10, or with 10 bits, you'd have numbers between 0 and 1023. So I'm actually going to show you what I'm talking about. I'm not going to do a huge 1024 type deal in this video. We're just going to do something small. We're just going to use 4 stations, which in essence is 4 bits. And how it works in binary is, station 1 is going to be what we call the least significant bit. It's going to be the smallest number, and so it is quite literally going to be a 0 and a 1. Off will be 0, on will be 1. And how it works in binary is, every bit you add into, or every bit you go up from your least significant bit, you double the value of that bit. So since station 1 is technically a 1, station 2, its value will be 2, station 3's value will be 4, and station 4's value will be 8. And all it is, say station 3's value is 4, so if it's on, you add 4, if it's not, you add 0. And that's how it works. And just using these 4 bits, we're actually going to have 16 combinations. We'll be able to go between the number 0 all the way to number 15, just using the 4 stations. First, there's 2 different things we have to do. We have to have 2 toy boxes, obviously, in order to use, or to prove that this station is actually working. And so I'm going to put a toy box door down. And the first piece of this video is going to actually be on how to read those numbers off of the station receiver. So we're actually going to go into the second toy box first, and we're going to do the read, because the read is actually quite a bit easier to do than the writing, because we're basically having to design a logic to write our counter down as binary. I'm actually not going to do that. We're going to do it in a different way, but we'll get to that part. So first, we're going to just go through this door, and we'll go to our second toy box. Alright, so in the second toy box, we're going to put down a second satellite receiver. we're going to take advantage of the fact that we know what numbers each of those triggers represents. So like I said before, in binary, the least significant bit equals 1. And so station 1 is 1, station 2 is 2, station 3 equals 4, and station 4 equals 8. And with just those 4 numbers, we can actually add up to any number between 0 and 15. So what we're going to say in this toy box is if station 1 is turned on, I'm going to send an increment plus 1 to this counter. And I'm going to say if station 2 is turned on, I'm going to send an increment plus 2 to this counter. If station 3 is on, I'll do an increment plus 4. And if station 4 is on, I'm going to do an increment plus 8. Now you might see why I'm not going any higher. I'm actually probably going to do a second video later. Not today, but later I'll do a second video on what to do if we're going higher numbers, because if I was using station 5 here, since the number always doubles, after 8 it would be 16, and if I go over to the counter, well, in Disney Infinity 2.0 you can only increment by 10 at the most at a time. So we'd actually have to build a little circuit to make it increment by 10, and then quickly after that increment by 6 again, so that it would equal to 16. So we're not going to do that in this one. We're just going to do a simple little counter like that. And I'm actually going to also put a quick little button in here. And all it's going to do is every time I push it, it will increment that counter. And that is just to demonstrate when I come back in here that I can continue to use this counter after it reaches the number that I want it to. I'm just going to say increment plus 1. Now I'm just going to go back to the first toy box. That's all we needed to do in here. Alright, so we're back in the first toy box, and I'm just going to add a counter to here. And in this toy box, the counter is not actually going to be providing us the binary count for sending the proper number over to the next toy box. It's just more going to be used as a visual display so the user can see what their count is. What we're actually going to be doing is we're going to be using something else that is also quite similar to binary, a logic gate, because you can open and close it. So it also has 2 states, which works perfectly for binary code. And actually, let me put this somewhere where it might make a little more sense. I'm going to put down one logic gate for each of the stations we're going to be using. And the idea behind this is that this logic gate is going to be station 1, going to be controlling our least significant bit, and then this station gate, or this logic gate, will be doing station 2, station 3, station 4. And what we're going to be doing is we're going to be inputting a signal. Every time our count goes up, we're only going to input into our least significant bit logic gate here. So really, all we're doing is we're adding 1 every time. And so what we're going to say is if it's open, then it's going to send an output when you send an input. So if it's open, it's a 0. And you've received an input, so that means you want it to be 1. So I'm going to turn on station 1, which means if you send in the input and it comes out input blocked, that means I want it to close. So I'm going to turn off station 1. And then I'm going to take a response from these guys, saying that if my station 1 turned on, it came out of output. So I actually want to close this logic gate so the next time it will come out input blocked. And if station 1 is turned off, I want to open this logic gate. So I'm actually using the logic gate to turn on the station, and then the station itself to switch the logic gate to the opposite state that it was just in. Now the next important part is the fact that if my logic gate is set to closed, or if the number in the binary code is 1, and we add another digit, then we need the next binary number in our sequence to turn to 1 while our least significant bit is changing back to a 0. So basically, if we're at 0 in our count and we get an input, it will turn on this station gate so that its bit is on, which will close this logic gate. So we are at the count of 1. If we get another input, we're going to come out input blocked, which will turn off the least significant bit. It'll turn that back to 0, but it will also send an input to the next logic gate, the one that represents the number 2, which right now is off, and it's going to do the same thing. It's going to send if it's open, it will send output to station 2 to turn it on. So now we have number 2 represented in binary. And we will do the opposite. If its input is blocked, turn off station 2. And of course we want station 2 to control it back. So if station 2 turns on, close that logic gate. And if it turns off, we want to open that logic gate. So what we're doing here is in binary we're adding 1, and the first gate here is going to change every single time you send an input because it is just a 0 or a 1. So if you add 1, that state has to change. And what we're going to do is we're going to tie all these logic gates together so that if pretty much every gate before it is set to a 1, so if this bit is 1 and this bit is 1, that actually equals number 3, and the next time we get an input we need the number 4. This logic gate equals 4, or this bit equals 4, so we'll need these two gates to close, or these two gates to be set back to 0, which is open, and this one will turn on, turning on station 3, which will mean that the count is just 4. I hope I'm explaining this well. You could look up binary if you want. If not, just send me a message or something and I'll try to explain it a little better. But that, in essence, is how binary works. So I'm going to do that from the next gate, where an output turns on station 3, and an input blocked turns off station 3. And when station 3 turns on, we want to close this logic gate. When it turns off, we want to open that logic gate. Now, I did not add yet the input blocked to the input of this gate, and it's going to work the whole way down exactly the same. As the count goes higher and higher, every time every logic gate in a sequence turns 1, the next one in the sequence will finally turn 1, and all the ones before it will turn to 0s, and then the count will continue. This one will turn on, then this one will turn on, this one will turn off. It's exactly how binary code looks. So, did I? Yes. And now we'll just do the last logic gate. We open it. And if you were adding even more bits in here, you just keep going down the chain doing the exact same thing, because it would keep incrementing in the proper order. So what we're going to do here is that should be all set up. And I'm just going to add a button. What we're going to say is whenever we press this button, the counter is going to go up by 1. And now the counter is not tied to anything. This is just, like I said, a visual display to the player of what the count is. The important part here is that every time the count goes up, I send input to the least significant bit logic gate, so that every time it'll keep going down the chain and incrementing and changing the bit value of the 4 stations in the satellite receiver. So we're going to give this a quick try. I'm going to hit this button, and I'm actually going to put it to the number 11. And I'm choosing the number 11 because if you know binary, 11 would actually be 1011. So it's actually 3 of the 4 stations will have to be closed for 11 to work. And we'll now proceed into this next toy box and see if our count is set to 11. There you go. Our counter is set to 11. Just because it knew that if each station was on, it knew which value to add to the counter. So it knew station 1 was on, so it added 1. It knew station 2 was on, so it added 2. It knew station 3 was off, so it did not add 4. And it knew station 4 was on, so it added 8. And that added up to 11. So our counter knows that we had a count of 11 in the last toy box, and we can start adding to it here in our next toy box and continuing on with our count. So that is how we can actually use the satellite receiver as a 10-bit memory register if we want, and how you can pass bigger numbers through to different toy boxes if you feel like it. I hope that was helpful, and I will be doing another video later on where we will expand into much higher numbers and see how we will send those to the counter.